Hello and welcome everybody to this webinar. One more webinar speaking about EMS in Inventor. Today we're going to be talking about electro-thermal analysis in EMS in Inventor. Dr. Ahmed Saeed will be the instructor and the presenter on that. So I'm going to go ahead and make him the presenter. This presentation should last about 30 to 40 minutes. After that, we can open the floor to questions. However, if one has a question, a few gentlemen have a question, meanwhile, you feel free, to stop even before the end of the demo, the webinar, and ask your questions. So welcome everybody, and let's go ahead and make Dr. Ahmed the presenter. There you go, Doctor.
Okay, thank you, Adam, and welcome to the series of webinars by EMWorks. Today's topic is electro-thermal analysis in Autodesk Inventor. Now, once again, the electromagnetic analysis or electro-thermal analysis is now part of Inventor. So I'm not going to go now over all the capabilities of the software, but I'll emphasize mostly on the electro-thermal part of it. So this is your regular Inventor model. So you create your model in Inventor, and again, since this is an add-in or to Inventor, you don't need to exit or import or export or heal geometry. You're right inside Inventor. So you click on the EMS Feature Manager and you start your analysis by using the so-called study the design scenario or a what if scenario or a case or a simulation. So I'm going to create a new study now. Now EMS comes with 5 modules, and all of them coupled to the thermal analysis. So while magnetostatic is you have a DC current or DC voltage and or permanent magnets. So usually you can compute forces and torques, capacitance, inductance, saturations, all of that design parameters using the magnetostatic. Electrostatic is an electric field solver instead. It's mostly you have insulators and you have a voltage difference. You want to see if you are the amount of electric field produced in the insulator. And this module can help you study and avoid corona and sparking and the electric breakdown. Electric conduction is again electric field solver, but now instead of insulator we have conductors, and the conductors you want to find the current flow and as well as the temperature rise in the conductor due to ohmic losses or Joule effect. The AC magnetic is a magnetic field solver, and now unlike the magnetostatic where there is no time variation, everything is static, the AC magnetic there is time variation, but limited to time harmonics, so currents are voltage sinusoidal. Furthermore, the AC magnetic, because of the variation of the current and or voltage with respect to time, there are so-called induced current. And Faraday's law tells us that there is induced current and eddy current. So with AC magnetic, we can study eddy current, skin effect, proximity effect, so on and so forth. So Now, talking about the thermal part of it, when you do the DC or magnetostatic, the only losses are actually ohmic losses. So only a heat source is coming from the winding or the coil itself. Now, when you do AC magnetic, yeah, you're going to always have the heat generated by the ohmic losses in the winding or the coil. In addition, you're going to have other losses, eddy current losses, or even core losses. They all contribute to the temperature rise in your steel and the surrounding. The transient magnetic is again a magnetic field solver, but now it's more general than time harmonic sinusoidal, where the current or voltage dependence can have any shape or form. It can be sinusoidal again, or step, or pulse, or exponential, or any arbitrary current time or voltage time curve. Right, so let's, for this, what we have see in front of you is called a graphite heater. And now I'm going to say coupled to thermal. All right. Okay. As you can see, it's called study 2. I can rename it to any name. And now we have the feature manager, what is called a study. I created a new study. Okay. So let me probably hide this. So this is what's so-called graphite heater. Graphite heater, where you can inside you can put liquid or sand or any other product that you can heat using the graphite heater. Now the graphite heater will have two sources of losses. In this case, you're going to have the losses due to the applied current as well as the eddy current. Of course, we can also add to it core losses. So let's start applying materials. So this is the graphite heater. I'm going to apply material to it, and let's say I'm going to apply probably mild steel. Okay. And as you can see, now I have the EMS material library that comes with many materials, literally hundreds of material, but of course we cannot cover all the materials because there are thousands or even hundreds of thousands of material. So these are the basic ones, but if you want to have more, you can very quickly, just 2 clicks, you can add your own material library and you use it over and again in future analysis. All right. So now I can notice that I can apply the material without closing the material database dialog. So instead of each part, I could have hundreds of parts for that or components. Said apply, open. And really, it remains open. So if I want to apply now to the next part, I can maybe I can choose some ceramic material and say apply, and then if I want to, there's an air outside, okay, and air apply, and now if you want to, this is the last one, say apply and close. All right. So what is different about this? In addition to being fully integrated in Inventor, our electro-thermal solver is also integrated together. So usually some other software vendors, they make you do the electrical analysis, be it AC or any other type of analysis. Then you have to export the file that has a heat load on the nodes, close the program, open another thermal program, and read in the data and do your thermal analysis. We do it differently. Okay. So as you can see, when I do load and restraint, well, I have the regular electromagnetic boundary condition with normal flux if you have a phase where the flux is normally applied. And now I also have a full-fledged thermal solver. Now, on the same model, I can apply the boundary conditions or restraints. So, okay, so or I can use the toolbar for that matter. Okay, so now I do convection. Okay. Now, one important part that you don't need to worry about applying the heat load due to Joule or ohmic losses or the core losses, eddy losses. All of them are applied automatically for you. So most of the time, if you don't have an additional heat source, who knows, maybe you could have this whole graphite inside a fan producing heat, or you have you put it in the whole part in an environment where you need to apply additional sources. Otherwise, you simply say convection. Now, the convection part of it, let me, 1 second, let me go back. I'm going to make the air visible. Okay, so the surrounding air, so I can say convection, and now my surrounding air, okay, is what is going to cool the graphite heater and all around it. Now, specify the convection coefficient and the ambient temperature. Okay. Now, the question is, can we specify a time-dependent or space-dependent convection coefficients, like in the fluid case? And the answer is no. For now, we simply we assume that you already have a convection coefficient, and we don't take into effect the speed or the velocity of the liquid. So you have to specify the convection coefficient as well as the ambient temperature. That's all you need to do. Okay. Note that in the graphite heater, the heat is a desired outcome, right? So in some other, as I'm going to show you later on, you could be designing around the heat. You want to maybe avoid the heat, like in transformer, or in this case, in a heater situation, you want to actually have more heat, more temperature. Okay. So how do you apply the excitation? Now, the only excitation now we have is the current excitation of voltage, or so-called coil. Coil we refer by coil is any conductor carrying a current, or it has a voltage difference across its limits. So now I'm going to say solid coil, okay, and this is my coil. Say that the current is going to, so let's specify, in addition to the part that represents the coil, I have to decide how the current is going to flow. Okay, so in this case, it's going to flow from, so all of these faces, okay, are, okay, and turn it around, and now this is the current is going to exit. This is a very simple example where, okay, then I specify the RMS current, so 1000 amps, and the phase. And actually, in this case, the phase really doesn't matter at all for the heat problems. That's all I need to do. That's it. And mesh it, and then run. So let's go and see a problem where we actually have a solution. So this is my graphite heater, Actually, in this case, actually the current is going to go from this face and exit from the other face, so you're going to have a loop. Okay, it's a little bit different from what I applied. So, all right, so as soon as it successfully solves, okay, you're going to have many folders all related to the results. So first one is the results table. So let me, okay, in the results table, you have electrical parameters, energy, storage, the flux linkage, current, voltage, inductance, impedance, and losses. In this case, the only loss they have is actually the losses in the graphite heater and the sand inside the heater that I'm trying to heat. So it's only ohmic losses. You could have, again, as I said earlier, other type of losses. Okay, so close. Okay. What else you can visualize? In addition to what we call tabulated data or lumped quantities, now you can look at the magnetic flux density, magnetic field, the current that you applied, the current that you induced, current density, which is induced current density, and in the winding is really the sum of both the applied and the induced current or eddy current. You could look at the electric field. You can also plot loss density and temperature. All right, so you can look at the electrical parameter, then you can look at the temperature gradient, the heat flux, so on and so forth. So because this is a field solver where actually Maxwell's equations are solved for the magnetic field, from the magnetic field we derive all other quantities, be it the eddy current or fluxes or flux linkage or inductance or any other quantities, and the temperature as well. They're all related to the amount of losses and current loss in the winding or in the heater. Right. So the first thing you can look at is actually the magnetic flux density. So I'm going to plot all right, so I can make this one larger. Well, that's the magnetic flux density, okay, and now let me go back and show the visibility, okay, and show the material inside that we are heating. Okay. Now, I think we had last webinar we had was mostly about visualization. I'm not going to go in details in visualization, but in addition to the fringe plot, you can actually plot the vector. Okay. All right, so as you can see, that's my circulations or the magnetic flux density in the graphite heater. Okay. Now, more importantly is looking at the current density, which is the sum of the applied as well as the eddy current. So let's plot the current density. Why it's important to see the current density? Because the heat rise is really going to be proportional to the amount of current circulating. So that's the amount of current circulating in the graphite heater. I can change, do a, wait a minute, I can do a, okay. I can zoom in, okay. So that's, as you can see, most of the current is around these corners. Okay. And then also I can plot the loss density, ohmic loss density, apply. Okay, so that is the ohmic loss density, and I can do ISO clipping to actually see where I have the maximum amount of loss. Okay, as you can see, most of my losses are on these corners. Okay. Well, then after you examine the current density as well as the losses, you can now look at the temperature, and you will see it is going to be proportional to the amount of losses in the material, so this is the temperature distribution. Now, maximum temperature is 143 degrees C. Okay. And I could also do, if I wanted to, let me see. If I want to see the heat temperature distribution only in a certain part, I could also do a 2D plot of the heat. And the transformer model is really the other way around. You want to minimize the heat. Okay. I'm going to go to EMS. Okay. In this particular case, in this example I have, the steps are the same. Okay. Except now in this example, in addition to the ohmic losses, I have core loss. So I apply the material that has actually core loss. So when I look at the results table, you're going to see when I look at losses, so all kind of losses are there. So the ohmic, the eddy, the hysteresis, the excess loss, and core loss. And all of these quantities, you can print them or export them to an Excel sheet or text file. Okay. Now, if I look now at the current now, as you can see, okay. Showing most, of course, of the current in the winding. So what I actually can do is I can isolate the core, because that's what interests me more. Thanks to Inventor, it allows me to actually isolate and look at only the core itself. So if I double click, now I can see everything else is hidden. They can see the current, okay, density at this particular phase, okay, which I could actually, okay. Now, actually, that's the applied current density. What I wanted to actually see is the total current in the core. All right, and this is a vector plot showing you how the eddy current circulates in the core region. Okay, and then you could look at the eventually, of course, you can plot all type of losses. Okay, in this case, if I want to plot 3D, I can plot any of these losses, so the ohmic, the eddy hysteresis. Now, why it's important to plot them? Because if I want to minimize or the temperature or maximize it, it's always proportional to these losses. So these temperatures are not coming from nothing; they always come from the losses. So if I want to change the temperature profile, I have to be able to either increase the losses if I want more heat, or manage to decrease losses by using different material or avoiding sharp corners. So different techniques to do that. So this is the loss density. And then the temperature. Here we go. All right. So I'm heating this core to about 61.42 degrees C, which is for a transformer, it's pretty hot. Okay, so I can do a section clipping, and again, I'm not emphasizing in this presentation on the post-processing visualization, because we had a whole webinar about visualization. Okay, it's, by the way, it's recorded. You can always go to our website and listen to it. But you can take a cross section, or you could even have up to 6 sections altogether superimposed in the same plot. So you could also plot the temperature gradient. Okay, and temperature gradient, of course, gets to be a vector. So that's your temperature gradient. Okay, and most of the gradients, you see them around the small air gaps. Okay, heat flux also, you can plot it. Okay, and the other thing that I wanted to do earlier is to plot the 2D plot to be able to see the temperature on a. Let me see if I can bring this. Okay, so if I want to plot, say, between this point and this other point over here, I can specify whatever units, and now I can do a 2D plot. It has the advantage of looking at the data as numbers, actually, instead of just looking at colors, where you have to go back and forth between the color chart and the plot itself, the graphics itself. Okay, you can zoom in, zoom out. Okay, and then you can track actually the. Now as I go from, this is point 1 on the segment is point 2, and now I can track the value of the temperature. Okay. I can see that in a text file, text format. So now there is no need for you to do the mapping between colors and numbers. It's all not always easy to do that. That's why we have this nice tool that actually allow you to look at the actual numbers. So these are the position, and that's the temperature. You can, of course, export it to a text file. You can print it. You can do a lot of things with this 2D plot. By the way, all of them, any of these portable data on the mesh, whether it is the flux density or current, losses, temperature gradient, any one of them, you can readily plot it on a segment, or segments, by the way. If I want to go back and say, okay, look, I don't just many different segments. If I want to go back temperature and do 2D plot now, again, I'm not limited to 2 points, right? So I can do this, that, this point over here, this point over there, and so on and so forth. There's no limit on the number of points. So that's also important to mention. Okay. So in this case, going to go back to the heat flux. So if for instance I look at my temperature or the and actually temperature gradient, and see there is a big jump in the temperature between one point to another, then if I look back and plot the losses, I'm going to see the same behavior, because the temperature is really directly proportional to the losses. Okay, so whether you want to generate heat for your design as heater or many other applications, or inductive heating for that matter, or you want to avoid producing heat like a transformer or motor or many other applications also, you can do that in the integrated product in the Inventor, where you in the integrated environment, you apply your electric characteristic as well as a thermal, and you will be able to see your all of the electrical and thermal quantities all in the same plot. And if you want to make small change, maybe you could, if you want to make just a small change, you don't need to, obviously you don't need to redo the whole thing, because you can copy the whole study, and now I can paste my study, right? So I'm going to go to study 1, and now if I want to change one of the parameters, I don't need to apply all the coils or apply all the materials. It's just now it's copying it. In the copied study, you just go and change whatever quantities, parameters, be it material or the current, and, or any other parameter in the study, and then you can, here you go, now I have my study. You can go ahead and run that study, or you could generate many different studies, and before going home in the evening you can run all studies, and when you come in the morning you find all the results, and then you can pick and choose your best design, best results. Now, last but not least is, once you do all of your electrothermal analysis, you want to document your work. So because there are many input and output, and so it's important to document your work, and you don't need to take a print screen or plot, print each graph, plot by itself. We automate the report generation for you. So we define a report where you can have you can customize your report by specifying the company logo, company name, company, and all of that, and you can pick and choose which section to include or exclude. So by checking different paragraphs, you have an option between an HTML and Microsoft Word file. Let me choose Microsoft Word file now and say OK, and now it's going to generate for me a Microsoft Word file inside Inventor, and that's again, it's another integrated part of it, because now you don't need to exit to open a Word file. Really, in the same model, you can look at the geometry, the CAD, the results, as well as the report. It's copying all the electrothermal results and the input geometry information, all of that in a nicely formatted Word file. Because it is a Word file, you can of course always edit it. This is my file. All paragraphs are so my materials, load, restraint, coil information, study properties, losses. This is in the impedance matrix, and then the plots. These are the magnetic flux density, magnetic field intensity. This is applied CAN density, all plots are right there. Because it is a Word file, you can obviously generate a PDF file if you wish to. So, okay, to sum up, then it's in EMS, in Inventor now is using a EMS. You can actually do either just a simple electrical simulation or electro-thermal, or you can even just do a thermal, by the way, application, because you could really, if I apply zero current, I can maybe apply volume heat, which I can use it to just to do a thermal problem without the electric part of it. But it's not. This product is not meant for that. There are other products which are more optimized to do just a pure thermal problem. But this is really more to quickly be able to look at the the losses and the temperature, and you can correlate between the losses and the temperature. Okay. The question is, what is excess loss? Okay. So basically, the core loss. Okay. Now, the core loss, physicists break it down to three types of losses. One is called the eddy loss, is clear. Hysteresis loss is clear. And there is another part which is, it's neither eddy loss nor hysteresis loss. So it's called excess loss. Okay. And the core loss is really the sum of the three of them. That is what is the excess loss. Some other mechanism of losses different from the eddy and hysteresis in the core, that's called excess loss. Does that answer your question, sir? Okay. Any other questions? Now, I think the floor is open for questions right now. Okay. I have two questions here. What is the mechanism of generating the excess losses? Okay. Well, it's really the core loss itself. If I apply, if you go back over here, and actually go to this material, edit material, and the core loss, you can see I have from your material manufacturer, I have what is called the core loss curve. Okay, where in the x-axis you have the B, and the y-axis you have the loss. Okay, in watts per kilogram. Okay. Now, what happens is, if you want to come at the core loss point at any point, and you want to break it down to different components, you want to see, you will be able to, and there are formulas for that, you will be able to extract the eddy losses and the hysteresis losses, but that is still going to have another part, okay, and that's what physicists call excess loss. So from where the excess loss coming is really from the core loss itself, when the property of the material and the that's where you're going to have the source of the excess loss is really as just a component of the core loss. Can you apply a frequency spectrum for ohmic loss? Well, really the yes and no. In the AC magnetic, okay, you really solve at one frequency, okay. But if you wanna do it to solve at many different frequencies, you have to do it in time domain, where you use a transient magnetic. In transient magnetic, you can have a different time step, and as you know, each time corresponds to a different frequency. That's one way of doing it, and while it's not the recommended way, because that's going to take much more time, because you have to work in time. Transient really is good and powerful at all of that, but really you have to wait, because you have to start from zero and keep working on time until you reach the desired time step or time position. Now, the other way is to copy your study, okay, and then you apply different frequency, okay, and then as you apply different frequency, the losses will be different, because the frequency is different. So if you have like 3, 4, 5 frequencies, then I'm going to have 3, 4, 5 studies by doing copy and paste or clone the study and specify different frequencies. Then at the end, I can see the effect of the frequency on the ohmic loss and eventually on the temperature rise. Any other questions? Well, if you don't have any more questions, I'm going to turn your attention to our website, Magnetic Works, and see you on the events, webinars. Stay tuned for future webinars. I will try to hold one on a weekly basis. So we have previous webinars are recorded, and I'm sure today's webinar, Adam is recording it. You can watch the previous ones, or stay tuned for future webinars, okay, and our different use and applications of EMS and the Inventor environment. You can also, if you want to look at some of the success stories, have testimonials. You can have many, actually you have hundreds of testimonials. These are happy customers, okay? Some of them actually are videos. You can say what our customers say about our software and how they were able to avoid the physical prototyping and bring their product to market faster using EMS. And the of course, we have another product. You see a product. We have also a high frequency. That's really mostly for very high frequencies, for microwave frequencies. But most of the application that for the electro-thermal is really come from the EMS, not the HFOs. Yeah. Even though even HFOs, you can have thermal, you know, if you have a maybe microwave heating. So please stay tuned and visit our website, and looking forward to seeing you in future webinars. And now I turn the mic to Adam. Thank you.
All right. Well, thank you, Dr. Ahmed, for your presentation. I would like to thank all the attendees again for attending this, making the time attending this demo, this webinar. And as Dr. Ahmed said, you're going to have some more coming, so we'll email you and let you know of them. Thank you again, and have a great afternoon. Bye-bye now.